Okay, just turn on the recording. So happy Easter to all. Let's start the lecture. Okay, where's the, okay, here we go. So let's briefly review last lecture's material on safety. So here's the outline, functional safety. So vocabulary: fault, failure, hazard, and risk. So for example, the last example, if a resistor in the power steering hardware breaks, that's a fault. And then it causes the power steering system to fail. That's a failure. So not all faults lead to failures. If a fault occurs in some parts of the system that's not important or is not related to the function, then the fault may be masked, so it may not lead to a failure. We only care about faults that actually lead to failures. And then a failure could cause hazard. So if you were driving at high speed, and then you might get injured quite badly due to the power steering system failure. So it's a hazard with a high risk. And functional safety refers to the safety of the system function. So, for example, the turn signal system shall turn on an indicator light telling the driver that the system is active. That's a function that must be working, as opposed to performance or non-functional requirements for reliability, dependability. So, for example, the turn signal system shall be available when the vehicle ignition switch in the on position. So that's a availability requirement, not the function itself. So functional safety only concerns itself with the functional requirements. And it only concerns with automotive electrical electronic system malfunctions, malfunctions. So, so it's not the nominal performance, but only if the function works or not. So for example, if the brake function is not engaged when it's supposed to, or if it's engaged when it's not supposed to, these are malfunctions. But if the braking distance, a vehicle traveling 60 miles per hour should come to a complete stop in 5 seconds, that's a performance requirement, not a functional requirement, not part of functional safety. So functional safety is more qualitative than quantitative. So yeah, so and also it only refers to E systems, not mechanical, chemical, or other systems. So functional safety analysis consists of 3 steps: identify hazards, evaluate the risk, and via systems engineering, try to lower the risk. So we're not discussing the last item. So well, we are discussing a little bit about the mechanisms to ensure functional safety. But our main focus is on identifying hazards and evaluating risk. So level of risk is dependent on the time. For example, seatbelts are mandatory today, but not 100 years ago. Hazards may be human error, technology error, or human-technology interaction error. So high levels of automation, L4, L5, will remove hazards due to human-technology interaction errors. So classify the causes for the following. Yeah, technology error is a software bug. Human error is a driver driving carelessly, going too fast. Human technology interaction error is when driver ignores warnings. If the warnings are too frequent, the system is too sensitive, it issues many false warnings. Then the driver may ignore these warnings. So this is a human technology interaction error. So that to mitigate this error, the vehicle detection system should be more accurate. ASIL, automotive safety integrity level, defines 4 levels from low to high, A to D. So D is the hazardous situation with the highest risk, while ASIL-A is the lowest risk. Below ASIL-A, you have QM, quality management. So which means that development according to accepted quality principles is sufficient to reduce risk. So typically this is done by the manufacturer, by the car maker within the company, whereas safety certification, according to ISO 26262, typically is done by outside certification authority. So ASILs are then determined by HARA, hazard analysis and risk assessment. So to evaluate risk, 26262 defines the risk as probability of occurrence times severity of the harm. So this is the generic definition of risk based on earlier standards, and ISO 262 refined it to 3 terms, but here we have 2 terms. So these are rankings, not actual probability numbers. So for example, here, driving on a snowy mountainside, probability is relatively low, so it's ranked as 2. And power steering malfunction may cause fatal injury, so the severity is relatively high, ranked as 4. So the risk is 2 times 4 equals 8. And then ISO 262 refined the definition. So ISO 262 standard is a very large document detailing every step from concept to product development at different levels, and to supporting processes and so on. So it's a very tedious and costly process to perform high levels of safety certification. So the model is a refinement of the typical V model for product development in automotive industry. So now we have 3 Vs. The V at the the V at the system level is the big V, going from here to here and back up here. The big V represents the overall system. So going down means that specifying requirements and going down to design. And on the right, going up means that product development and up to operation. And 2 small V's represent subsystems. The left one represents the hardware development, right V represents software development. So if you flatten the V model, you have a linear process from the first process, concept phase results in a functional safety concept. So the term concept in ISO 262 is synonymous with document. So it's a really functional safety document. And then at the development phase, you perform a hardware development, software development, the two little V's, and followed by safety validation and functional assessment. And finally, after release, that after production, you gotta have operation support and maintenance. So here's the overall process, starting from item definition. That is, what is this functional item about? Is it about lane keeping assistance, or is it about power steering? So what is this thing? And then after you identify the item, you specify safety goals for this item. And then to realize the safety goals, you produce a functional safety concept document with a list of functional safety requirements, FSRs. Then you allocate the FSRs to architectural elements. So maybe functional safety requirement 1 is mapped to element 1, and FSR2 is mapped to element 4, for example. And then you refine the functional safety concept to a technical safety concept. So that is a more fine-grained specification of requirements. And then you allocate TSRs to a more fine-grained system architecture, specifically sensors, ECUs, actuators, and so on. So it's allocation of TSR to architectural element at a finer grained level than allocation of FSRs to a more abstract architectural elements. We'll see examples of those later. So HARA involves situation analysis, hazard identification, and then hazardous event classification for its severity, and determine ASIL, and finally you obtain a safety goal. So so here's the overview of the terminology. Item is a high-level system, for example, lane keeping assistance system. A system is a set of elements. A subsystem is a smaller piece of the system. Component may be an ECU, sensors and actuators with software hardware parts within each component. So this example is a running example throughout the lecture. So lane keeping assistance consists of two functions, lane departure warning and lane keeping assistance. Lane assistance system, the overall system consists of two functions. So if a driver departs a lane without using a turn signal, the system assumes that the driver has become distracted and did not mean to leave the lane. So driver should be driving in the center of the lane. So should be driving in this direction. So suppose somehow he's sleepy, he drives, on the side, not in the center of the lane. Then two things will happen. First, LDW function will vibrate the steering wheel to provide the driver a haptic feedback to remind the driver, hey, you're off the center of the lane. LKA function will move the steering wheel so that the wheels turn towards the center of the lane. So to provide some help to the driver. So now look at the LS system. We're supposed to derive ASOs for the system. So here's a decomposition of the LS into systems, subsystems. So situational analysis, that's where people sit around and brainstorm about hypothetical driving situations. So here's driving on the mountainside. And then what are the possible malfunctions? Brake failure, a typo here, brake. Control unit short circuit, bit flip, airbag deploys unexpectedly. So, and then to provide help to people in systematically deriving these requirements, you have tables of guide words: function not activated, function unexpectedly activated, and so on. And tables for hazardous events. So none or front collision with oncoming traffic, and so on. And then you just fill in the blanks. So for RAS example, you fill in the blanks as operational mode, normal driving, on a operational scenario, highway, during environmental details, rain, hence slippery road, with a high speed, situational details, and item usage, correctly used system. So for example, after brainstorming based on the tables, you get, for example, this hazard for the lane departure warning. So the malfunction, maybe the actor effect is too much. That is, the oscillating torque on the steering wheel is too much so the driver cannot maintain control of the vehicle. So that's one hazard. So here's another hazard identified for LKA. So the malfunction is that the driver takes both hands off the wheel because he trusts the function too much. He misuses the function by taking both hands off the wheel and treating the car as an AV, causing LKA function to be always activated. So the malfunction may cause a hazardous event, that is collision with other vehicles. So after you identified the malfunction, so now look at the this workflow there. With the situational analysis, with the hazard identification, the next step is hazardous event classification based on exposure, severity, and controllability. So here the risk definition is refined from the previous definition. Probability of occurrence, that corresponds to exposure, severity of the harm, that's to severity. And then because ISO 262 is specific to automotive systems, it added controllability. So the tables show the ranking of severity from S0, no injuries, to S3, life-threatening or fatal injuries, to E, exposure, 5 levels, E0, incredible, and E4, high probability. And controllability has 4 levels, C0, controllable in general, and C3, difficult to control or unable to control. So these are documents from the standard. So for example, normal driving on a highway during rain, slippery road with high speed and correctly used system. This is the situation we identified previously. Now let's identify its severity, exposure, and controllability. Severity, pretty high, highway driving, right? So we rank it as S3. Exposure, medium probability. So the situation, driving in the rain on the highway is not uncommon, not every day. Controllability, we rank it as difficult to control or uncontrollable. So if the steering wheel vibrates too much, it is difficult to control the vehicle. So given the three rankings, we can do a table lookup from the standard document. We have SOC for this function of lane departure warning. So other driving situations, driving on a wet road on a city street at low speed. Now the LDW function is SOA. Severity is S1. Exposure is E3. And controllability is C3 as before. So S1, E3, C3. If you do the table lookup, S1, E3, C3, that's SOA right here. So so the driver is driving more slowly with all other conditions remaining the same. So therefore, severity has gone down. The risk has gone down due to the severity reduction. So the overall ASIL is reduced. Driving on the dry road on the city street at low speed. So now it's a dry road. Exposure is higher because assuming the city doesn't rain very often. Now ASIL, overall ASIL is ASIL-B. S1, E4, C3, that's right here, ASIL-B. So it seems paradoxical because driving on a dry road has a higher ASIL than driving on a wet road. So the reason is mainly due to higher exposure. A driver is more likely to be driving on a high road than a wet road. So there is a higher probability that a random malfunction will occur on a dry road, hence risk increases for the dry road scenario from ASIL-A to ASIL-B. Driving on a dry road on a highway at high speed. Now severity pretty high on the highway. Exposure E4, controllability C3. Lookup table, you get ASIL-D. And finally, if more than one situation maps to the same hazard, choose the highest ASIL level. So if you are trying to determine ASIL level for LDW function for highway driving, regardless of wet or dry situations, then the overall function is ASIL-D, the maximum of the dry scenario with ASIL-D and wet scenario. I think this is not a very good example. What is the ASIL for the other scenario? Yeah, I think I should function for city driving is ASIL-B. Yeah, that's probably more appropriate because we determined that driving on the wet road has ASIL-A, driving on the dry road has ASIL-B. So driving regardless of wet or dry road is ASIL-B, the maximum among the two ASILs. Okay, any questions? So it's you should note that ASIL is not equal to importance. Often people mistakenly and simplistically think that a higher ASIL function is more important. That's not necessarily true. So importance, the word itself does not really appear in the document ISO 26262. So for example, consider two safety functions, SF1 and SF2. SF1 is SOC, S2, E4, C3, S2, SF2 is SOB, S3, E2, C3. Now, SF2 has a lower ASIL due to its higher lower exposure E2, but its severity S3 is higher than S1's S2. So loss of S2 may cause more severe harm than loss of S1. So the loss here is a little bit confusing. I should say malfunction. So SF2 is assigned a lower ASIL mainly because its exposure is lower, so it's less frequent than SF1. It's used not so frequently, but if it's used, then its malfunction is more severe than malfunction of SF1. So you cannot say that SF2 is less important than SF1 just because it has a lower ASIL. So we determined the ASILs pretty much by human intuition. So why did we determine the severity as S2 instead of S3? So it's all hand waving. So there are more formal methods for determining the various factors. So for higher ASILs, there are formal techniques such as fault tree analysis, which is mandatory for SOC and SOD. So for hardware failure rate, SOD needs to requires hardware failure rate to be less than 10 FIT. FIT is number of failures expected in 1 billion hours of operation. SOBC require hardware failure rate of less than 100 FIT, and SOA requires hardware failure rate of less than 1,000 FIT. And software units with SOD require more rigorous testing, like MCDC coverage, whereas SOB only mandates DC coverage. So these are testing, software testing terminology. So now we have gone through from situational analysis, hazard identification, hazard event classification, ASIL, and now we are ready to define a safety goal. So for the hazardous event, LDW function applies too high an oscillating torque to the steering wheel. We derive a safety goal, that is the oscillating torque from the LDW function shall be limited. So safety goal for LKA function among the four choices. Remember the hazard was that the driver was mistakenly treating the LKA function as autonomous driving. So he's not controlling the vehicle. So the safety goal is that it shall be time limited and additional steering torque shall end after a given time interval so that the driver cannot misuse the system for AD. So that's the safety goal for LKA. So here's the summary of HARA. So we identify the malfunction and perform hazard analysis. What kind of hazard could happen? And risk analysis, how likely is the hazard to happen? That's exposure. How harmful is the hazard? That's severity. And how controllable is the system if the hazard occurs? That's controllability. And ASIL determination based on the 3 factors. And then you determine the ASIL to be levels of A to D. Okay, so after HARA, we need to write a document, the functional safety concept. So the document includes deriving the functional safety requirements, refine the item architecture, allocate functional safety requirements to the item architecture, determine ASILs for the subsystems. So based on information from HARA, we identified 2 malfunctions for the LDW function. First, it applies an oscillating torque with very high torque amplitude above a certain limit. Second, it applies an oscillating torque with very high torque frequency above limit. And we add one malfunction for LKA function. It's not limited in time duration, which leads to misuse as an AD function. So there are formal safety analysis methods for deriving safety requirements, identifying conditions and causes that could lead to requirements violations, and identify other hazards not identified in the HARA, including FMEA, HAZOPS, FMD, EDA. So these are tools used by safety engineers. So we're not going to cover these in this course. We'll just use some basic logic to derive functional safety requirements. So based on the 2 safety goals we identified before, one is limiting the oscillating steering torque. One is time limiting the LKA function. So we derive functional safety requirements, FSRs. So from functional safety goal 1 of the LDW function, that is the lane assistance item shall ensure that the lane departure oscillating torque amplitude is below max torque amplitude. And for the second goal, we have another FSR, except this is limiting the oscillating torque frequency to below max torque frequency. So corresponding to the previous 2 malfunctions. One is on amplitude, one is on frequency. We identify the 2 requirements. And for the LKA function safety goal, this safety goal, we identify this FSR, the lane assistance item shall ensure that the lane keeping assistance torque is applied for only max duration. So you can see that FSR is more concrete than the safety goals. Safety goals are just they're more vague. It just says that steering torque should be limited, but FSR actually specifies concrete numbers for how much they will be limited. Similarly, for LKA function, it specifies a concrete time limit, max duration. So we have the FSRs defined. You have 3 FSRs, 2 for the LDW, 1 for the LKA. Now we need to allocate the FSRs onto the architectural elements. So here's the architectural diagram. You have the camera subsystem with a camera sensor, camera ECU for performing perception tasks, maybe a GPU for deep learning. And you have a power steering subsystem that is taking as input the steering wheel torque and computing a output to provide a torque to the steering wheel. So it's a feedback control system. And then the car display system is car display ECU interacting with the car display. So that's for human-machine interaction. So now we suppose we allocate the 3 functional safety requirements FSRs to the electronic power steering ECU. Then the FSRs become the electronic power steering ECU shall ensure that blah blah blah. So if you look at the previous 3 items, I should highlight the 3 items. A lane assistance item, so that's the overall item. And then in the next, after the allocation, you refine it to actually the ECU shall do something. That's for the allocation of the 3 FSRs to the ECU. If you allocate it to some other architectural element, then you have a different subject. So now you have requirements to architecture allocation table. So for FSR1, the electronic power steering ECU shall ensure that the lane departure warning oscillating torque amplitude is below max torque amplitude. And then it's allocated to the ECU, not to the camera ECU, and not to the display ECU. So that's why I have a cross here. And you have a row for each FSR for the allocation. And then you have architectural requirements. So the ECU, electronic power steering ECU, we refine it into 3 parts. So to implement the requirements, we add software blocks to each of the ECUs. So a camera sensor ECU has lane sensing and torque request generator, and car display ECU has lane assistance status. Lane assistance are active, inactive, and power steering ECU has lane assistance, analyze driver steering torque, and final electronic power steering torque output. So this is in preparation for the next step for final grain allocation of safety requirements. So in this example, we're assuming that this FSR shall allocate it to software blocks to automotive EE components. It's also possible to implement FSRs with mechanical components instead of software blocks. So ASIL inheritance. So we have the 2 FSRs One is on the oscillating amplitude, one is on oscillating torque frequency, and then because they are derived from the original more abstract FSR, oscillating torque shall be limited, and that safety goal, I'm sorry, that first one is safety goal, and then the two lower ones are the FSRs. So the safety goal has SOC as we determined before. And then the FSRs inherit the same ASIL, SOC, from the safety goal. So now the ECU, power steering ECU, the red box, inherits SOC from the two functional safety requirements. And no functional safety requirements are allocated to the camera sensor and car display subsystems. So they're not relevant to a functional safety analysis and are assigned QM. So they're not a part of the functional safety process. So here's my little, had a little puzzle. So the allocation is to power steering subsystem instead of the power steering ECU. So because a sensor and actuator, here motor is the actuator, these in combination with the ECU form the power steering subsystem. So I think that the functional safety requirements allocation should be should be allocating the requirements to the entire subsystem. But you know, people sometimes when we talk about ECU, it implicitly includes the relevant sensors, actuators, or the peripherals. So maybe they are referring the whole thing, but it's, you know, it's a particular a chip plus peripherals. So from the figure, you can also see that the sensor is SOC, ECU with the three software blocks. Each one is also SOC, and actuator is SOC. So it is allocating SOC, assigning SOC to the sensors, the ECU, and the actuators. So ASIL decomposition can be used to lower ASIL. So for example, an ASIL D subsystem, ASIL D overall system can be decomposed into two redundant ASIL B subsystems. So if you assume that the failure modes are independent for the two subsystems, then you can do a simple probability calculation. If each subsystem has probability of malfunction as 0.01, then the overall system has probability of malfunction as the product of 0.01. So we got 0.0001. So, and then perhaps the probability of malfunction is too high for each subsystem to be certified ASOD, but their combination may be certified as ASOD. So it's also a motivation for sensor fusion. Typically, individual sensors may have a certain failure rate, probability of malfunction. That's not enough to be certified ASOD. But if you have redundant sensors or redundant computation systems, then the overall system may be certified at ASOD. So if you do ASIL decomposition, the subsystems are labeled as ASIL-B parenthesis D. So the parenthesis indicates the parent ASIL before the decomposition. It's a little bit redundancy here, parent ASIL. So here's the ASIL decomposition rules as defined in the standard. So ASIL-D may be decomposed into a ASIL-D subsystem plus a QM subsystem, or ASIL-C plus ASIL-A, or ASIL-B plus ASIL-B. And similarly for other decompositions. So it's a very effective approach for reducing safety certification complexity. For example, for the ASIL-D decomposition, you may think of the dual checker architecture, where the ASIL-D subsystem is a very simple checking logic that's easy to certify, and the QM subsystem as a complex, difficult to certify subsystem. And then you can, instead of certifying the entire system as ASIL-D, you can focus on certifying the very simple subsystem for ASIL-D. So ASIL decomposition for our running example. So this on the left we have the ASIL allocation of ASIL-C to every architectural element: sensor, ECU, software blocks, and actuator. Now, we want to reduce certification effort with ASIL decomposition. So we take the lane assistance functionality, this box, and refine it into two software blocks. One is normal lane assistance functionality. One is safety lane assistance functionality, which is a simple check to limit the magnitude of torque. And then we, after decomposition, we assign QM to the normal lane assistance functionality, which may be a very complex piece of software with deep learning, with all kinds of weird software. It doesn't matter because it's QM, plus a very simple logic to simply limit the torque to a maximum magnitude, certified as ASIL-C. So because the safety lane assistance functionality is so simple, just a few lines of code, it's very easy to certify. So this decomposition significantly reduces the burden of system design and analysis for ASIL-C. And the rest of the elements are still the same, all ASIL-C. So, but we took a very complex piece of software out of the ASIL-C level. Okay, any questions? So now let's look at the system timing. Obviously it's a hard real-time system. The fault tolerance time interval, FTTI, for FSR refers to the time it takes to detect and react to a malfunction. So for example, for FSR1, the power steering ECU shall ensure that the lane departure oscillating torque amplitude is below max torque amplitude. So the fault occurs when the vibration, the oscillation, torque amplitude exceeds the given threshold. So from detection of the fault, you up to handling of the fault to reach a safe state. So you have two time intervals. One is diagnostic test interval, that's amount of time needed to detect the fault. One is fault reaction time, amount of time needed to react by setting the vibration torque to 0. perhaps done by the safety module of limiting torque, or done by within the software module itself. So thus reaching a safe state. And then this overall time is called FTTI. It must not exceed the time until accident could happen. So suppose this is the potential accident time from the fault to the accident. That is the torque amplitude is too high, causing the driver to lose control, causing the car to have an accident. The overall time is the time until accident could occur. And then the FTTI, the sum of the two green intervals must not exceed the time until accident could occur. So say 50 milliseconds. I just put a number in here. So this should be determined based on vehicle speed, road conditions, a lot of factors. Yeah. Okay, so any questions? So let's take a 5-minute break and come back at 2. So that's FTTI for system level timing constraint. And warning and degradation concept, it's another document that discusses how the driver will be warned of a malfunction, what the system will do to degrade the functionality, i.e. to take the system to a safe state and recover from a safe state. So gradual degradation versus turning a system off. So the two functions we have been discussing, LDW and LKA, are not critical for driving a vehicle. So if the system has a malfunction, we can turn them off to make the system take the system to a safe state. So it's not a AV, it's a driver assistance system. Therefore, human driver is available, so you can simply turn off the LDW or LKA functions. And then human in control, that's your safe state. So turning off the system is not the only option. Some systems may provide limited functionality and degrade to different levels depending on how bad the malfunction is. So for example, a car engine control system, if one sensor fails, the engine control system might reduce the torque output of the motor so that the vehicle can still be driven, but at lower speed. Uh, so this degrades the engine control subsystem to a safer but functioning state that would help the driver avoid getting stranded. So if you simply turn off the engine control system when one sensor fails, then the vehicle is stranded on the road. So for the human technology interaction in case of malfunction of functional safety requirement 1 or 2 of LDW, turn on the warning light to the driver. So this is implemented by adding a software block lane assist malfunction warning and a connection from safe lane functionality to it. So here's the bird's eye view of the functional safety analysis workflow. So you start from the item definition, you do HARA and obtain a set of system goals, each with a assigned ASIL level. And then you come up with functional safety requirements, FSRs, that inherit the ASIL from its corresponding safety goal. So the ASIL here is the same as the ASIL here. And then you allocate the FSR to subsystem architectural elements. And then in this safety concept document, you specify for each FSR, you specify the fault tolerance time interval FT, TI, driver warning, degradation, turn off or degraded functionality, and safe state. For lower levels of autonomous driving L2 or below, safe state could be a human in control. For higher levels of autonomous driving L4, L5, because human is not in control, the safe state may be a degraded function state implemented by some other system. So you cannot rely on a human anymore. And then this particular requirement has all the attributes, ASIL allocation and a bunch of other attributes. And same is true for every FSR. And then the next step is the techno safety document requirements. So I had an extra slide in the online, which should be removed. So TSR is a lower, more concrete set requirements, which we'll discuss in detail. So TSR, I think that slide really belongs to later. So let's, I'll revise the slides. The functional safety concept is the last step in the concept phase. So that phase results in a document called functional safety concept. And then after that, based on this document, we start the next phase of product development. So it's divided into two parts. One is the product development at system level, to come up with a technical safety concept document, and then product development at the hardware and software level. So a technical safety concept involves two steps. So first, turning FSR into a TSR, technical safety requirements, for each of the subsystems. So we have a camera subsystem, display, and power steering. And then allocate the TSRs to the system architecture. Yeah, so that figure belongs here. So that was my fault. I should really delete it. So in our running example, the only safety relevant element was the electronic power steering ECU or power steering subsystem, including the sensor and the actuator. So our TSR will go directly to the ECU level. But in general, you will need to develop multiple technical safety concepts, one for each safety relevant subsystem, and then one for each safety relevant ECU. So here's the general scenario where you have the specification of technical safety requirements in the technical safety concept, and then you allocate the TSRs to different subsystems. And then subsystems may be nested. So you may have subsystem B1, B2 nested within subsystem B. And then after allocation of the TSR, you design the subsystem architecture to implement the TSR. So functional safety requirement is more abstract and high level than technical safety requirement. So for example, the lane keeping item shall ensure that the lane departure oscillating torque amplitude is below max torque amplitude. For a technical safety requirement, it's more concrete and describes the signal flow and which component is in charge of the functionality. For example, the LDW safety component shall ensure that the amplitude of the LDW torque request sent to the final torque component is below max torque amplitude. So this can be implemented by using LDW torque, setting LDW torque request to 0 if it exceeds max torque amplitude. But we're not concerned with implementation yet. So this is the implementation. So you have normal lane assistance functionality, which outputs a primary LDW torque request, and then it may be unsafe. It may be too much and cause to excessive oscillation. And then the safety lane assistance functionality takes as input the primary LDW torque request and puts a bound on it or sets it to 0 if it's too much. And then the output LDW torque request is guaranteed to be safe, regardless of how large the primary LDW torque request is. But this is the implementation of system implementation. At the TSR stage, we're still at the requirement stage. So we're just saying that this particular safety component shall ensure that amplitude of LDW torque request should be below max. It doesn't say how it's implemented. So additional categories of TSRs, for example, detecting faults within the system, the validity and integrity of the data transmission for LDW torque request signal shall be ensured. So maybe the signal is transmitted over an in-vehicle bus, and then we need to specify the transmission malfunctions. So that's additional TSR resulting from the more abstract FSR. So one FSR may result in multiple TSRs on different aspects, computation, transmission, network transmission, and so on. So another category of TSR is detecting faults in an external device interacting with the system. So for example, the anti-lock brake ECU might send a vehicle speed data to the electronic power steering ECU, and then you may use CRCs, cyclic redundancy checks, or live counters to detect fault in the data transmission. So so the vehicle speed is sent from the anti-lock brake system to a lane assistance item, and then you add additional checks for the communication errors. So you can allocate TSRs to these check blocks, software blocks. So not covered here, but you may try it at home. Perhaps you won't. So the reason we're discussing this additional block, which doesn't appear before anti-lock brake system, is because the lane assistance system really needs to take into account driver speed to decide how much torque to apply. So so if the vehicle is traveling at high speed, then if the lane assistance item vibrates the steering wheel too much or turns the steering wheel too much, that's a lane assistance item, not the LDW. So if it turns the wheel too abruptly at a high vehicle speed, or it provides too much extra torque on a sharp turning curve, then the driver could lose control of the vehicle. So exactly how much is too much is dependent on vehicle speed. Maybe this turning is safe for low speed, but not for high speed. So that's why we need the vehicle speed input from another module, anti-lock brake system. So this could be part of HARA, which may lead to another safety goal, FSR and TSR. So by taking into consideration the anti-lock brake system in addition to the lane assistance item. But we're not discussing that part here. We're just focusing on the lane assistance item. So another category of technical safety requirement is reaching a safe state. So as soon as a failure is detected by the LDW function, it shall deactivate the LDW feature, and LDW torque request shall be set to 0. That's the safe state of turning the system off. So number 4 is implementing a warning and degradation concept. As soon as LDW function deactivates the LDW feature, the LDW safety software block shall send a signal to the car display ECU to turn on the warning light. So that's the ECU we saw before at this position. It's not drawn here. So number 5 is preventing latent faults. A memory test shall be conducted at startup of the EPS ECU to check for any faults in memory. So by adding this memory test at startup called safe startup module software block, and then it can prevent any latent faults due to memory faults. So all these are additional TSRs derived from the more abstract FSRs. So here are TSR examples. So from the same FSR, the lane keeping item shall ensure that the lane departure oscillating torque amplitude is below max torque amplitude. We derive four, shown here, we derive 4 TSRs. First is that the LDW torque request should be below max torque amplitude. Second is that the LDW safety software block shall send a signal to the car display ECU for alerting, informing the driver that LDW has been disabled. Number 3 should deactivate LDW feature and set the torque request to 0. Number 4 to ensure the validity and integrity of data transmission in case the data is transmitted over the bus. And each TSR, similar to FSR, you have FTTI and ASO level. In this case, the 4 TSRs all inherit the same SoC from the corresponding FSR. And finally, the memory test TSR has ASO-A. So because the standard document says that latent fault detection for SoC requirement can be labeled ASO-A. So it's not critical to the operation of the function. So it's ASO-A. And FTTI is ignition cycle. So every time you turn on the vehicle, it's checked at startup only once, not periodically like the other functions. So that's refinement of FSR from FSR to TSR. Any questions? So we have the TSRs derived. Now we need to allocate the TSRs to the architectural elements, specifically software blocks within the ECU. Remember that we allocated FSRs to architectural elements, specifically the EPS ECU. That's an allocation on a more abstract level. Now we're allocating the TSRs at a more concrete level to the specific software blocks within the ECU. So here we have LDW safety functionality. So let me see. We have memory test ASO-A. So I think the keeping the steering torque to below max is allocated to LDW safety functionality. The other TSRs, there's a data transmission check TSR integrity check that corresponds to a TSR number 4. And that's allocated to a software block right here. So that's SoC, inheriting the SoC from the TSR. So yeah, so remember we had the ASO decomposition. So the normal lane assistance functionality is this QM. It's not safety relevant. The TSR is allocated to the safety functionality. So this is allocation after allocation of TSRs to the software blocks. And on the left, you have everything QM for the camera and the display subsystems. So elements inherit the highest ASIL from the technical safety requirements. So if the same software element provides functionality to the LDW function, which is ASIL C, and the OK function, which is ASIL B, then the higher ASIL wins. So the software element is assigned ASIL C. So if an element contains sub-elements with different ASILs, then both sub-elements receive the highest issue. The exception is if the criteria for coexistence is met. That is, if a failure in one sub-element will not affect the other sub-element, the sub-elements can have different ASILs. And then the internal and external interfaces for safety-related elements need to be clearly defined, so non-safety related elements are clearly identified as well. So now we move to the last item, functional safety for hardware and software. So we have done a lot of requirements engineering, FSR and TSR. Now, after so much requirements engineering, finally we're ready to develop some hardware and software to implement the requirements. So here are the two small V's we saw before. On the left is the hardware product development cycle, from specification of hardware safety requirements to hardware architectural design, to evaluation of hardware architectural metrics, and evaluation of safety goal violations due to random hardware faults. That's going down the left, and going up to the on the right is integration and testing and verification of hardware safety requirements. So there's horizontal checks at each level. So similarly for software. So the general idea represented in each V stays the same, similar to the system level V. First, you specify safety requirements, then you allocate these requirements to system architecture. Finally, you test, integrate, and verify. So on the hardware side, in the hardware V, it includes sections about hardware architectural metrics and evaluation of random hardware failures. So that's specific to the hardware V. For software, there's an architectural design section, as well as a unit design section. So a unit is a smaller part of a software architecture, could be a driver to read raw data from a camera sensor. So the V's look roughly the same, except with a few specific steps for hardware and software. So here's a bird's eye view of what would be involved in a functional safety project. So you you stretch out the steps of the V model vertically. So sometimes an item may have multiple systems and subsystems, and subsystems will have their own software and hardware requirements, and these subsystems need to be integrated into larger systems. So you start from initial product development, specification of the technical safety requirements, and then that's up to the TSR level. After the TSRs have been identified, you go to system design, maybe dividing the system into multiple subsystems. And then for each subsystem, you specify the TSRs, allocate TSRs, and actually develop the hardware and software. That's coding, programming, and then you do integration and testing, and repeat the same process for every subsystem. And subsystems may be nested. And finally, you go up on the right branch of the V cycle and perform integration and testing, and eventually to a vehicle integration and testing. So random hardware failure. Yeah, I mentioned this before. So that's the FIT. So I think I should delete this slide. Yeah. Okay. So for software development, programming languages commonly used in automotive software is C, C++, and MATLAB. Obviously, MATLAB is for control design with automatic code generation to C and C++. So software development guidelines include Mishra C and Mishra C++. These are industry standard guidelines that specify a subset of C or C++ for safety critical applications, including defensive implementation techniques. Always check for array bounds, always check for null pointers, all that checks. And language subsets. For example, recursion is generally disallowed in Mishra standard because it may cause unlimited recursion and cause memory exhaustion. So you can only use a subset, a safe subset of C or C++. Style guides and naming conventions. So Mishra stands for Motor Industry Software Reliability Association. So generally, Mishra standard is used by automotive software engineers. So we have TSR. When we develop a software, we need to allocate the TSRs to a software safety requirement, SSR. And then allocate the SSRs to software architectural elements, to more specific software routines within each software block. So here are basic requirements allocated to software elements, and safety requirements allocated to safety software elements. So for example, the safety software element may be a checker routine that checks the range of the LDW torque does not exceed a upper bound. If it does exceed, then limit the magnitude of the LDW torque output. And then the software that implements a basic requirements, not a safety requirement, may be a very complex piece of software, maybe involving deep learning components. Whereas the safety software blocks are generally very simple and easy to verify. So freedom from interference refers to the requirement that failure in one software element does not spread and cause failure in other software elements that communicate with it or run on the same ECU. Maybe between software elements with the same ASIL or different ASILs. So here's a pictorial illustration of failure spreading from one element to another. Could be between a ASIL-B software element and ASIL-B in another ECU, or between ASIL-B software element in one ECU and ASIL-D element in another ECU. So all these should be prevented. So especially from ASIL-B software element, the fault spreads to ASIL-D element. That's not a good idea. So Yeah, I think this is not very clear. I should really add a big cross on each. Uh, yeah, I'll do it later. So the basic idea that uh, these should be not allowed. So spatial interference could happen if memory address spaces of software elements interfere with each other. So you may prevent it by partitioning the memory address space. So a counter example is when a software element with QM level has a bug that creates a pointer to the memory address space of a software element with SOC level. So it writes to a memory address that's shared with the SOC element, causing a safety goal violation. So that's an example of spatial interference. To mitigate this problem, so we can partition the memory address spaces so that they will never share any common memory address. It could be done by using software processes inside of threads. Processes have different virtual memory addresses that are separated from each other. So if you have a operating system that supports software processes, then you just allocate the software elements with different ASIL levels to different processes. Problem solved. But oftentimes, a smaller ECU cannot afford to have software processes. The operating system is too simple. It only supports threads within the same process. Then you need uh, other mechanisms for partitioning the memory address. But a specific mechanism is not important. The idea is that you should try to prevent this kind of spatial interference. So temporal interference is, for example, blocking of execution due to some shared data. So perhaps this piece of shared data is grabbed by the software element here, and it's a lower priority thread. And then the higher priority thread software element cannot access the data that's blocked for a long time. So that's one example of temporal interference. Another one is deadlock due to circular waiting. So software element A is holding a resource A and requesting resource B. And software element 2 is holding resource B and requesting resource A. So it's a classic deadlock scenario. And neither can make progress. And on the bottom, you have incorrect sensor fusion due to incorrect clock synchronization between software elements. So the radar and camera sensor data, their clocks are not synchronized well. So the sensor fusion fails. Because if you're fusing the multiple sensors, you need to correlate the sensor data with the correct timestamp in order to detect a particular object based on both radar and camera. The data should be from the same time instant. Therefore, these two clocks should be synchronized. So more cases of temporal interference, so incorrect allocation of execution time and incorrect execution of a sequence. So for this example, you have a correct execution scenario where the software task is executed 3 times, perhaps a periodic task, and then if you execute it 2 times or 4 times, they're not, then it's not correct. So the correct execution is that it should be executed 3 times, perhaps in a given time period. So you can check this execution for its correctness by adding a checkpoint at every step. And if the so every time a software task is executed, you increment a counter, and at the end of the time interval, if the counter is 3, then it's correct. Otherwise, it's incorrect. So middle, you have deadline monitoring check. So if a software element is executed before its deadline, then it's a correct execution. Correct? And here is incorrect. Deadline is not drawn here. Perhaps deadline is somewhere like here, in here. And the lower execution exceeds the deadline. On the bottom, you have control flow monitoring to ensure that, to check that software elements are executed in the correct sequence. So software task A, B, C, D, that's a correct execution sequence. If you have A followed by Z, or B followed by C and D without A, then both of these are incorrect executions. So you can check for those again with checkpoints. So for communication interference, so communication channels between ECUs often have QM level safety certification. So these are in-vehicle bus protocols such as controller area network, CAN bus. So these are typically cannot be certified at a very high ISO level because they have certain failure rates which may be too high. So given this low ISO level communication channel, how do you implement higher ISO? So QM for communication channel, whereas ISO-A for software elements that depend on the communication channel. So you can add end-to-end protocols, blocks within each ECU to detect errors due to transmission errors. So could be based on CRC's cyclic redundancy checks mechanism, so that if you detect an error due to data corruption on the communication channel, you simply discard it to ensure that any data passed up to the application software element is correct. So you can view this as a form of ISO decomposition, whereas a QM communication channel combined with ISO-A end-to-end protection module results in the overall higher ISO. So let's look at a particular example, eGas. eGas is a software architecture design pattern commonly used in the German automotive industry. So it divides the system into 3 levels. Level 1 is the functional level, which implements the system functionality. And then with 2 additional levels of monitoring. Level 2 is for functional monitoring that monitors level 1 for safety goal violations. And if level 3 is for processor monitoring that monitors the hardware to ensure that it didn't fail. so you can think of level 2 as monitoring the software for software malfunctions, where level 3 monitors for hardware failures. That is the hardware being dead, that kind of failure. Whereas that transient hardware failures may cause software bugs, may cause transient outputs that are wrong. These are detected by level 2. So level 3 is essentially monitors for aliveness. And then on the lower figure, you'll see a level 2 monitoring. If it detects a safety goal violation, then the output from level 1 is disabled. So you send issue a disable signal to this block, which will essentially disable the level 1 output. So for example, you can set the torque to 0 if level 2 monitoring detects a violation of the torque bounds. So the eventual output to the steering wheel is within safe limits. Okay, so that's the end of our chapter on safety certification. So any questions? We have a few minutes before we start the next section. So the next 2 classes, I will discuss a new chapter on control, because I wanted to give out the assignments today on control design. So we'll discuss the Intel responsibility sensitive safety part later. So there's a slight deviation from the a slide from the PowerPoint sequence. So okay, so before we take a rest, any questions on this chapter? Okay, everybody very quiet. So I guess everything is crystal clear. Yeah, so this lecture, this part on safety is really what safety engineers at automotive companies do every day. So safety engineering is a very tedious task. It's a lot of requirements engineering, a lot of paperwork, a lot of requirements traceability, and so on. But somebody's got to do it. Okay. Since you're so quiet, let's take a break for 10 minutes and come back at 2:58.